Well, good afternoon. Thanks for being here this afternoon. We have another session today of our PAThlestra, and today we have Miguel Jorge. He's a professor from the University of Strathclyde in Glasgow in Scotland. He has been working with us. He's an expert in molecular simulation, and he has been collaborating with me, Germain, Emmanuel, and other people that are doing molecular simulation. With Richard as well, but Richard couldn't be here with us today. And he's going to present his works and some developments. I hope that you enjoy it. I know that this is very much far away from what many of you are doing, but I guess that what we have been doing during these last years has already convinced everybody of the value of molecular simulation to understand the things that many of you are doing. So, without further delays, let's pass to Miguel and listen to what he has to tell us today. Thanks, Miguel, for being here with us today.
No, thank you for the invitation to do this seminar, and of course to Mariam for putting everything together and teaching me how to work with Microsoft Teams. Hopefully things will go smoothly and won't crash and burn after 5 seconds. So I'll tell you about a bit of my work, recent work on trying to model thermodynamic properties, improve prediction of thermodynamic properties by taking into account polarization effects. Before I do that, some of you may be wondering already, João has mentioned this, but what the hell is a Strathclyde? And the Strathclyde University is in Glasgow, so it's not Glasgow University. There are two main universities in Glasgow. Strathclyde is the other one. Glasgow is the largest city in Scotland, but not the capital. The capital is Edinburgh. The campus is right in the city center. I have this very nice picture of Glasgow. Of course, normally it doesn't look like this. It looks more like this. But as we were just saying, we're in the middle of a heat wave with minimal amounts of rain, and so I'm feeling almost like tropical weather at the moment. So this slide gives you a brief summary of research I've been doing over the years, and it's all applying molecular simulation. I'll explain a bit more about what molecular simulation is. But these are the main applications. So a lot of the work we've been doing is focused on porous solids, be it in predicting adsorption performance for gas separation, gas storage, etc., or trying to understand how these materials are synthesized and trying to use multi-scale modeling to describe and to predict how the material structures are formed. And that also is linked to surfactant self-assembly, formation of micelles and mesophases, etc. We've also done some work on fluid interfaces and probing fluid interfaces at molecular level, which is more challenging than can be imagined at first sight. And finally, there's been some more recent work on predicting solvation-free energy solubilities and partition coefficients of small molecules, small but complex, multifunctional drug molecules, etc. What I'm going to talk to you about today is not any of these topics, but it's something that permeates across several of these because it's quite fundamental. It goes back to the fundamental level of molecular modeling. And so the outline basically is I'm going to start with a brief introduction of molecular simulation and force fields, which are the models that underpin all of these calculations, and then go into a bit more detail about polarization interactions, what they are useful for, and then discuss how we can incorporate these polarization interactions into conventional force fields to improve the way we predict bulk phase and mixture thermodynamic properties. Okay? In particular, I'm going to talk about dielectric constant as one of the properties we're interested in, and also about solvation-free energies as a second type of properties. Okay? And then I'm going to wrap up with some conclusions. So to begin with, molecular simulation basically works by putting together a bunch of molecules inside a simulation box. And then the molecules are starting to interact with each other, and they collide and move around, etc., according to some physical laws. So that is essentially replicating microscopic states on the computer. Then from those microscopic states, we can use statistical averaging techniques to calculate macroscopic properties, namely thermodynamic and also dynamic properties, which we can relate to experiment. Okay, and this transition, this link between the micro world and the macro world, is essentially given by statistical mechanics, which is a theory that encapsulates this notion. Okay, so in a way, statistical mechanics makes the link between thermodynamics, macroscopic thermodynamics, and the realm of quantum mechanics and the world of molecules and atoms. Okay, and in fact, some people call statistical mechanics as statistical thermodynamics or molecular thermodynamics. There's, some people who call it that. So that's the underlying theory. I won't spend a lot of time to explain what it is, but essentially you can think of this as molecular simulation being a computer experiment, a virtual experiment, in the sense that once we specify the rules by which the atoms interact with each other, we can let the simulation loose. It evolves in time, as does a normal experiment. And then we can average properties, just like we do in an experiment, to obtain some quantities that we can measure. Okay. So the key in any simulation, therefore, is to establish the links between, or the interactions between every atom and molecule in the system. And that's what we call a interaction potential or force field. Okay, so essentially we have the molecular model, which is a force field, tells us how so it approximates the way molecules and atoms interact. And then based on that, we can run a molecular simulation method, which is nothing other than a numerical integration method. Okay, kind of similar to finite element methods, for example, used in fluid mechanics. So we can use this integrator to then propagate the system in time and then calculate averages of thermodynamic properties. So going back, so this lecture is essentially not about the method, but about the model. Okay, so how do we model these interactions between atoms? So the first thing to understand is that in a system with many atoms, typical of condensed phases like liquids and solids, the total interaction energy U is a sum of pairwise, 3-body, 4-body, etc., many-body interactions. Okay, so for example, for a 3-body term, the interaction on particle I depends on the presence of particle J and particle K together. So there's kind of an interaction between all 3 particles at the same time. And then you can multiply this, okay? Of course, that's impossible to compute. And so what people do in practice is we exclude all the many-body interactions, all many-body terms, and lump them all together into a binary pairwise, what we call pairwise effective interactions, okay? So essentially, what we say is, in the computer, in the simulation box, atom I only cares about the presence of atom J to calculate the interaction with atom J, okay, and so on. And so we sum over all the possible atom combinations. So that means that we need to represent the realistic interactions between atoms by way of effective parameters. So that's what essentially the creative part of modeling is, coming up with new ways of representing these interactions. So the table here shows a list of the most important intermolecular types of interaction that we might want to consider here. Okay, so for example, molecules or atoms can be bonded to each other through covalent bonds. That's the last term here. Of course, we are dealing with classical interaction models, so we treat these covalent bonds essentially like springs. Okay, I won't really go into this in a lot of detail. But it's a simplified way of representing a covalent bond, and then we can do the same for angles, etc. So when we start to look at atoms in different molecules, then we can think about repulsion as being the shortest range of interaction. So repulsion is when 2 atoms come very close together, their atomic orbitals start to overlap, and that leads to very strong repulsion. Okay, so it's very strong but very short range. The other, and it's ubiquitous in the sense that every atom undergoes repulsion. Likewise, dispersion, which is normally called also London interactions or van der Waals interactions, they are short range, but they're attractive, okay? Which means that every time 2 atoms approach each other, they induce dipoles in one another and they reinforce themselves in a positive way, leading to attraction, okay? So these also happen between every atom. Then electrostatics only really take place or are only really important for polar molecules, but they are very important for polar molecules. So what I mean by electrostatics is interactions between permanent multipole moments. For example, water is, as everyone I think knows, is a dipolar molecule, which means it has a very strong dipole because of the asymmetry between the oxygen atom, which is very electronegative, and so sucks up a lot of electrons, and the two positive hydrogen atoms. So that creates a dipole, which really completely dominates the behavior of water as a molecular liquid. So we have to account for these, and these are normally included as atomic point charges on the molecules. I'll show you in the next slide. But then the last term is the one in red, which is the one that this talk is mainly focused on, is polarization. Okay. So polarization is intrinsically a many-body interaction. And so what it means is that the molecules, the interaction between the molecules, changes depending on the environment that the molecule is in, namely whether it's isolated, or whether it's in a hydrophobic or non-polar medium, or whether it's in a very highly polar medium. Okay, so the surrounding molecules essentially create an electric field that changes the way the molecule behaves and the molecule interacts. Okay, now, as I told you, it's a many-body term, and so it's very, very expensive to calculate in a simulation. Now, there are models called polarizable models that do this, but this comes at a very high cost in terms of computational time. Okay, so in the best estimate, I think the computational time increases by a factor of between 3 and up to 10 times relative to a conventional model. Okay, so we want to avoid this kind of many-body computation if we can. Okay, so this talk is about how we can include these polarization effects into non-polarizable models. So I'll skip this slide about the bonds bending and rotation, etc., because it's not relevant. This is the typical potential model used to describe repulsion and dispersion. Okay, so they're combined together normally into this Lennard-Jones potential. Some of you may have heard about this. So this first term to the power 12 is the repulsion, which is positive, and then an attractive tail with exponent -6. And this is the form of the Lennard-Jones potential. So it has two parameters. Essentially, sigma is a size, which is the well depth, or the exclusion diameter of the molecule or the atom, and epsilon is the strength of interaction energy. Okay, so the larger the sigma, the bigger the atom is going to be. So oxygen has a larger sigma than hydrogen, for example. And similarly, the larger the epsilon, the stronger the interaction is going to be. Okay, so we can tune these usually to match experimental properties. So we adjust these values of the parameters for the atoms to match stuff like bulk fluid properties like density, enthalpy vaporization, vapor-liquid diagrams, etc. Okay. The electrostatics, as I said, is modeled through point charges, Q. Okay, this is just Coulomb's law. And this graph shows an example of how important these can be. So the black line here is the Lennard-Jones potential between two oxygen atoms in water. Okay. And then all these terms in dashed lines are the individual contributions of electrostatic interactions. So oxygen, 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 hydrogen, 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 etc. And if you add everything together, you get this red line, which is a total interaction between a hydrogen bonded dimer. Okay? So you see that the energy is in the vicinity of -30 kilojoule per mole. And it's completely, the Lennard-Jones contribution, the dispersion contribution, is completely overwhelmed by the electrostatic. Okay? So just to say essentially that in a polar system, if you don't account for electrostatics, you're doomed. Essentially, there's no way you're going to get realistic behavior. So polarization is much more expensive to compute, and therefore what happens is that it's implicitly included in some force field parameterizations by adjusting the point charges. I'll explain this in a bit more detail after. Okay, but it's not explicitly included because that costs time and therefore money. And these are just names of conventional, typical generic force fields that we tend to use that some of you may have been familiar with. Amber, charm, biomolecular force fields, BROMOS, TRAP, OPLS, etc., etc. So TRAP is a particularly interesting force field for us because it has been designed to describe vapor-liquid properties, which are particularly useful for chemical engineers. And so it's actually one of the more interesting force fields in the context of the work that we are doing. So, as you can expect, some of these models have serious problems. Okay, they are very good at what they are designed to do. So, for example, predicting a lot of typical bulk properties like densities and enthalpies, etc. But when you come to more exotic properties, perhaps, or properties that involve changes of phase, then the whole thing starts to become a bit dodgy. So this example here is related to the dielectric constant. So the dielectric constant, for those of you who are not familiar with this, is a value that measures essentially the response of the fluid to an applied external electric field. Okay, so it has to do with, for example, the ability of a fluid to act as an electrolyte, as a screening medium for electrolyte interactions. So it also can be seen as the screening potential of the medium. So, for example, water has a very high dielectric constant because it can screen charges effectively, whereas alkanes, for example, have very low dielectric constants because they are very non-polar. So you can predict dielectric constants. I'll show you how we can do this using molecular simulation. Several people have recently tried to benchmark the ability of molecular models to predict dielectric constants over a wide range of molecule types, a wide range of different force fields, etc. So these are 4 studies that I found in the literature. And with exception of the yellow one, which is only focused on molecules with hydroxyl groups, and I'll come back to this in a second, all the others cover a wide range of functional groups and a wide range of polarities. Okay? So the most striking conclusion of this study, of this benchmark comparison, or these, is that molecular models systematically underestimate the dielectric constant. Okay. Now, there's a lot of scatter, of course, and that means that the models themselves need refinement. I'll come back to this point, but the key point is that there's a systematic underestimation. So you can see the trend falls on quite a nice straight line, but it's much lower than the diagonal. Okay. So my theory is that this actually has to do with missing physics, and the missing physics is related to the polarization issues. Another example, and so I'll tell you later how we actually cope with this. Another example is the hydration-free energy, or any kind of solvation-free energy. So when you try to predict solvation-free energies of small monofunctional molecules, most models do a good job, right? So methanol, propanol, ethylamine, acetone, etc. They're fairly reliable. But when you mix and match functional groups in the same molecule, then the whole thing is hit and miss, essentially. You can get good predictions, or you can completely fail. In fact, I've seen, in some studies, that you can even get the wrong sign of the solubility. So that's quite serious. Okay. So I think, again, this has to do with polarization being missing in the force fields. And again, we're going to try to address that, taking small steps in that direction. So in order to break this deadlock, we need to actually understand what it is that happens to molecules when they are moving from a gas phase to a condensed phase, in this case, a liquid. Okay. So the experimental path, which I show here, is when a molecule goes, and just to explain the notation, a molecule is in the gas phase, G, when it's isolated, and it goes to liquid phase when it's surrounded by other solvent molecules. Okay. It could be the same liquid, right, in which case it's kind of self-solvation, but it could be a different solvent. What happens also is that the dipole moment, and further multiple moments, but the dipole is the most important, they change when a molecule goes from the gas to the liquid state because of that polarization effect. Okay, it responds to the electric field, and so it changes the dipole. So it goes from mu G to mu L. Furthermore, the molecule in vacuum is isolated, so the medium is vacuum. So that's epsilon 0 is the vacuum permittivity. And when you go to a liquid, it's actually sitting now, the molecule, in a bath of electrons. So you have a bath of electrons belonging to all the other liquid molecules that kind of screens the interaction or the polarity of the central molecule. And that's what I designate here by this epsilon infinity. This is the infinite frequency or high frequency dielectric constant, which is proportional to the square of the refractive index of the fluid. Okay. So this essentially measures the electronic response of the molecule, which again is not captured in these classical force fields. Okay. So the first step, we can decompose this experimental path in several steps, which is quite instructive. So the first step is to distort the dipole moment from a gas phase configuration to a liquid phase configuration. Okay. And this cost is an energy cost. So when you go from the gas to the liquid, it's a positive energy, which is unfavorable because you're distorting a molecule which is in its ground state. Okay, so you pay an energy penalty to do that. Then we can take the molecule, which is distorted now, and pop it into path of the electron. So now we have these electronic effects, which the model also doesn't account for, and it's going from the medium is going from epsilon 0 to epsilon infinity. Finally, we need to put this molecule, which is polarized, interacting with other molecules which are moving around. Okay, so now it goes from G to L. And this is precisely the term that we can easily capture in the classical simulations or molecular dynamic simulations. Okay, so this term we can handle, we just can't handle these other two, distortion and electronic effects. Okay. Another complication of this is going back to that issue of effective potential models, is that what we do in a classical molecular dynamic simulation is not run a molecule with liquid phase dipole moment embedded into a bath of electrons, because we can't do that. So in effect, we screen the dipole moment and we say, well, actually, effectively, the molecule behaves as if it had a lower dipole moment, mu m. M stands for model. Okay, so this mu m that typical, for example, water models have is not the same as the true liquid phase dipole moment of water. Okay, it's a screened dipole moment. I'll explain the implications of this in a second. So for the first term, the distortion energy, as I said, it's an energy penalty. It's been first derived an expression based on dipoles only, which is essentially a quadratic relationship between the delta mu, the change in dipole moment, divided by 2 times the polarizability of the molecule. Okay, so this is easy to compute, and it has been used by Berenson in developing the famous SPCE water model, if you're familiar with that kind of thing. There are now more rigorous expressions that go up to quadrupoles and later moments, which we are using also in our calculations. Okay, so in practice, this strongly affects prediction of phase change energies, because of course, if you take a molecule from gas to liquid, you must account for this distortion energy. Okay. However, it has no effect on the dielectric constant, because dielectric constant is already a bulk liquid property. Okay, so we don't have to take into account distortion in dielectric constant. The second term is this electronic term. Okay, so we can essentially apply something called the Born-Oppenheimer approximation, which is to say that the nuclear degrees of freedom, the molecule, the nuclei of the atoms, are moving much slower than the electrons. Okay, so we can account for the nuclear degrees of freedom in the simulation, but not the electronic degrees of freedom, because that's quantum. Okay, and we are not running quantum simulations; we're running classical simulations. So we can use some approximations. I'll explain this in a second, to calculate this term, this electronic effect term. And my PhD student, Andrew, has done some calculations recently for water. And it turns out that these two terms, the distortion and the electronic term, cancel out very largely. Okay. Again, I'll show you some data on this. So again, classical non-polarizable models cannot describe this component because it's an intrinsically quantum component, which we need to account for in a different way. And finally, we have this scaling effect, where the charges and therefore the dipole moments of the molecules are scaled from their real values in the liquid to the model values in order to provide useful thermodynamic properties. So we can represent this through a scaling factor k, which we may take as an empirical parameter, or we can derive from first principles. Now we're trying to do both. So I forgot to say that the electronic contribution now does affect the dielectric constant very strongly, because it affects the response to a field, and of course we need to take into account. This scaling also affects the dielectric constant, because the dielectric constant calculation is going to be based on the model dipole, but the real one measured in experiment is based around the liquid dipole. Okay, so we need to correct it also for that. So now I'm going to show you the two parts. The first is the dielectric constant corrections, and then I'm going to solvation free energy. So the first is the dielectric constant. The first formula here, without going into too much detail, tells you how the dielectric constant is calculated from a classical MD simulation. It's basically computed from the fluctuations, this term here is the fluctuations, in the total dipole moment of the simulation box. Okay, that's large case M with a subscript M for the model, because we use the dipole moment of the model. Okay. In reality, this is the experimental dielectric constant. We are not using the dipole moment of the model, but we're using the true liquid phase dipole moment, ML. Furthermore, we also need to account for those electronic effects through including epsilon infinity instead of 1 in the calculation. So one, it would be when the molecule is in vacuum. Epsilon infinity is when it's in a bath of electrons that respond to the field as well. Okay, so we have these two terms, these two corrections. We need to transform mm into ml, and then transform 1 into epsilon infinity. Okay, so if we combine these three equations, we can derive the expression that allows us to correct the simulated dielectric constant by way of the scaling factor and epsilon infinity to match the experimental dielectric constant. How we do this in practice? So epsilon infinity is an experimentally measured property, so we can just grab refractive indexes of all the fluids we're working with, square them, and we get epsilon infinity. Okay? We estimated K. K is a lot more tricky. So we estimated this by just fitting the dielectric constant of one molecule, methanol. Okay, so we're just fitting that, deriving the K value, and then extrapolating the same K to all the different molecules and all the different liquids we're looking at. Okay? So let me show you what happens when we do this. So this is that data set in yellow that I showed you before, in that cloud that I showed you of predictions. And now it clearly shows that there's a systematic underestimation. Okay, so these are all molecules containing OH groups. So we fitted K to one of these molecules only, methanol, which is probably somewhere here in this bunch. So the first thing we can do is we can add epsilon infinity. So small difference, but the difference is systematic. So you now increase all the dielectric constants by a nearly constant value epsilon infinity. So you can already see that the low dielectric molecules are now much better predicted than before. So you correct part of that systematic error. But the most important introduction is to include K. And this K, again, was determined for methanol and then extrapolated for all the other molecules. You see that by doing that, we completely eliminate systematic deviations in the data. Okay? So we're getting rid of these systematic deviations completely. Interestingly, the guys who did the systematic benchmark study of these alcohols also developed a new model designed to fit the bulk phase dielectric constant of methanol. And it turns out that their model, which is a tweaked model, an adjusted model, where they adjust the parameters to match dielectric constant, gives even worse predictions than we obtained by just using the scaling factor to the previous model. Okay? So importantly, this middle column here, the mean sign deviation, gives you an estimate of the bias. So the previous models all systematically underestimate the dielectric constant, including this second row, which is the tweaked model adjusted to match the dielectric constant. Whereas when we apply the scaling correction, we obtain something which is very close to zero. So we eliminate the bias, essentially. Okay. So now what happens when we apply this to systems which are much more demanding because they include many more varieties of molecules, acids, amines, alcohols, halogens, alkanes, etc. Okay? And we can see here that we get the same qualitative behavior. Again, the scatter is very significant, which means that even with the corrections, we have models that perform poorly for some classes of liquid. That's a different issue which needs to be addressed specifically for those liquids. But the key point is, again, the MSD is shown in brackets here. The key point is that by applying this correction scheme, we completely eliminate systematic deviations in the data for all data sets that we looked at. Okay? I think this is quite significant, which means that we are now including the correct physics by applying the corrections. So in very recent work, which we just submitted for publication, what I showed you before was for pure liquids. Now we can also look at, first of all, liquids over a wide temperature range, so different temperatures, but also, more interestingly, mixtures. Okay, so we looked at ethanol water and ethanol benzene mixtures over several temperatures, and without any fitting parameters, just applying that correction together with some very simple ideal solution mixing rules, we can just correct the dielectric constants of all these mixtures in a very effective way, okay, which is something that hasn't been achieved by any model in the past. So that was the first example, okay, applying this to dielectric constant. Now let's look at the solvation-free energies, okay? So I think most of you will be familiar with this idea. So solvation-free energy is essentially a measure of the free energy difference between a solute or a molecule in the gas phase and in the solution phase. And again, the solution could be a pure liquid. It could be the molecule being condensed into a pure liquid, or it could be a different solvent, in which case we have a solvation-free energy. If it's water, we call it hydration-free energy, but it's essentially the same thing. And this is a key property to predict solubility of pharmaceuticals, to predict partition coefficients, ligand binding free energies, etc. So the way we calculate this, very briefly, and if anyone has any questions, I'll be happy to answer them at the end. But very briefly, we do this by applying something called thermodynamic integration, which means that we are taking our solute, which is this green molecule here. It's solvated in the solvent, okay, these blue molecules, and essentially we're making the solute gradually disappear from the solvent. So the interaction between it becomes progressively weaker as we go to the right. And we measure the gradient of the energy, the gradient of the Hamiltonian. And then once we get to the point where the solute completely disappears, we can integrate this curve and obtain the total solvation-free energy. Okay? And we can decompose this in several contributions, but that's not important for this purpose. Okay, so this is a well-established method that we can use to calculate solvation-free energy. Now we're doing that, we're calculating these solvation-free energies, but we also need to apply those polarization corrections. So we have an energy for distortion and an energy for the electronic terms contribution, okay? So the sign of these will change depending on the direction in which we're moving our molecule. So for vaporization, we're moving it from the liquid to the gas. So for example, distortion term turns out to be favorable. But for solvation, which is what we're mostly interested in, it's unfavorable because we're moving the molecule from the gas to the liquid. Okay. So very briefly, we again calculate these terms through analytical expressions. This one I showed you already. We can use more complicated ones as well. For the electronic component, we use a very simple dielectric model, a Kirkwood-on-Sagar model, which is very, very simple. It's just a spherical cavity. The molecule is in the cavity, and it surrounds with interacts with the dielectric continuum with a dielectric constant of epsilon infinity, which is that bath of electrons. And so what we did was, as I showed you before, as I explained before, we applied this to water, and I'll show you some results of that. But more recently, one of my students, Cecilia, has applied this to the trap model for pure alcohols and mixtures of alcohols with alkanes. So we applied the correction to an existing model to see if that would improve the predictions. But we also did our own parameterization, which is what we call the Polka model for polarization consistent approach. And we reparameterized that to fit thermodynamic properties of alcohols. And then we test the transferability of this model for predicting other properties and properties in mixtures. Okay, so let's see what that looks like. So before I show the prediction results, these are the polarization correction calculations. Okay, so it's important to distinguish three different cases in different colors. So in the first case, we have polar solutes in very polar solvents. Okay, in this case, they're all the same, but it doesn't matter. If we do alcohols in water, the same effect is seen. Okay, so what we see is that the magnitude of distortion and the magnitude of electronic contribution is very large in both cases, but the magnitudes are very similar, and therefore they cancel out to a very large extent. So for alcohols, in fact, these corrections are almost negligible because they're within the margin of error of experimental measurements and even of simulation calculations. Okay, for water it's slightly larger, but really statistically it's within the error margin of 0. Okay. So it's very interesting that the two components are very large, but they cancel out for polar molecules. The second case for non-polar molecules dissolved in polar solvents, or in fact in non-polar solvents, both terms are essentially 0. And that's simply because the polar solutes are now completely non-polar. So therefore, their dipole moments are nearly 0, and therefore they don't respond to an electric field. Okay? So both contributions are 0, and you get a total correction of 0. The more interesting case is when you have polar molecules dissolved in non-polar solvents, in which case the distortion contribution is small, but the electronic contribution is just about the same. You'll see here, these three cases compared to these three cases. It's nearly the same as in a polar solvent, because a non-polar solvent also has this bath of electrons of this more or less the same interaction energy. So when you put these two together, it turns out you get a very strong negative contribution to the solvent. And that's what I'm going to show next when we look at the transferability of these models. So in these graphs, I'm showing you several properties as a function of number of carbon atoms in an alcohol. So these are linear alcohols, but we did also calculations for branched alcohols and so on. And the green are the experimental data points. The red are the results of our Polka model, which has been reparameterized to match some of these properties. The black is the trap model, and then the black full symbols are the trap model with the corrections. Okay. So for density, there are no corrections because it doesn't depend on polarization explicitly. And so trap and Polka give you fairly good predictions of density. Our model is slightly better, but not very significant. For diffusion coefficient, again, our model is a bit better. And again, polarization doesn't explicitly need to be taken into account. For the enthalpy of vaporization, we need to account for the corrections, but as I showed you before in this table, for these cases, they are very small. And so again, you see that the open and full black squares almost overlap together. Okay? And again, our model gives you slightly better agreement with the experimental ones. The more interesting case is, again, the dielectric constant, which confirms just what I told you before for a very specific system of alcohols, that when you don't include the correction, you get a massive underestimation of dielectric constant. And then just by including the correction, we improve this significantly. And our model actually hasn't been fitted to dielectric constant. It's been fitted to density, diffusion constant, and enthalpy of a few alcohol molecules. And it gives excellent predictions of dielectric constant throughout the whole series. The solvation free energies are perhaps even more interesting. So now we have the self-solvation free energy in this corner, which means the energy of solvating a molecule in itself. Okay. And again, like the enthalpy of vaporization, we have polar molecules in polar solvents. The corrections are very small. And so trap and trap corrected give you the same predictions. And both trap and our model give you good predictions of self-solvation, which is expected. Now we go to mixtures, and now we try to look at alkanes dissolved in octanol. And as I told you before, again, this correction here is strictly 0. So again, the trap and trap C overlap. And our model, again, gives you slightly better agreement, but not significantly. Where it does really make a difference is here, in the last case. This is alcohols now dissolved in hexadecane, which is a highly non-polar solvent. You see that if you don't apply the correction, these points here with the dashed line, then the model significantly overestimates the solvation free energy. Or in other words, the interactions are not as favorable as they should, because we are missing that electronic contribution to the interaction. If we now take that into account by using our correction procedure, then we get a much better agreement with experimental data. And again, our model, which was not designed to fit this, gives you even better agreement than the trap model with corrections. Okay. So the key message here is that if you want to use a model that has been designed for pure component properties, if you want to use that in a context of mixtures with fluids of different polarity, then it's really important to include these polarization corrections. Otherwise, you will very likely get things wrong. And we've just published that in Journal of Chemical Information and Modeling. So essentially, the final consideration here, which is where we're going in the future with this particular topic, it's worth thinking about what input we actually need to calculate these corrections. So we need several properties. First is alpha, the molecular polarizability. So this is measurable property. So people can measure it by actually precisely measuring the response to electric fields. So there's experimental data on typical molecules, but also you can do it by quantum mechanical calculations. Okay, so for more complex molecules, for example, we might use a QM calculation to get this. This is fairly straightforward. Epsilon infinity, as I told you, is also experimentally accessible through the refractive index. Okay, it can also be computed from quantum mechanics, although it's a bit more complicated to do. The dipole moment of the gas phase, so the isolated molecule, again, is something that is experimentally measured. So in the calculations I've showed you before, all of these three properties have been obtained from experimental data, in fact. Okay? Or you can also use quantum mechanics, and this is fairly trivial, to obtain the dipole moment in the gas. Now, the key quantity, however, is the dipole moment of the solid in the liquid phase. This is impossible to measure. Well, okay, impossible is too strong a term, yes. It's extremely challenging to measure experimentally. The only measurement that I'm aware of that is reliable, seems fairly reliable, is for water, using a combination of neutron and X-ray scattering from the structure factors of water. And it tells you that the dipole moment of water is about 3, roughly 2.9 dBi, compared to a gas phase dipole of 1.85, so almost a doubling of the dipole moment, and compared to dipole moments of classical models, which are around 2.2 or 2.3. Okay, so this is much higher than what the classical models expect. Now, these are really difficult to measure, as I said, and they're also really difficult to calculate, even using quantum mechanics or ab initio molecular dynamics. So what we're doing now, and this is work that I'm doing with Richard, is trying to come up with a quantum mechanical approach, which we call self-consistent electrostatic embedding, where we essentially surround our central molecules by a bath of point charges, and we adjust the values of the charges self-consistently. And that allows us to calculate the liquid phase multipole moments, which is exactly what we need to now use these corrections using only first principles data, without having to fit either the scaling factor or any of the other corrections to experimental data. Okay, so the idea is that we can now complete the loop and calculate all the properties we need self-consistently from theory, and therefore obtain a model which is completely predictive ab initio. Okay, and the preliminary results have been just submitted for publication. So the conclusions of the talk are that if you use, in many cases, in most applications, we actually need to use classical non-polarizable models. We can use better models or more more involved models like polarizable models, but you pay a penalty in terms of computational speed. Okay, but the price you pay with using classical non-polarizable models is that some properties will be off, systematically off, and that comes from missing physics in the model. So what we are proposing is an approach, a consistent approach that allows us to incorporate that missing physics without having to reparameterize the model and without having to use more complicated approaches. Okay, so it's very cheap to calculate, and we can do it after the fact, after running a simulation. So we showed that these corrections systematically eliminate systematic deviations in the dielectric constant predictions of existing models. They improve transferability of solvation-free energies when you mix and match solvents of different polarity. And what we hope to achieve now is this representing a new paradigm in molecular modeling, whereby you would really never go back to using a model that does not incorporate this type of correction, because there's no reason not to do it, really. So hopefully I've convinced you of that. And just to thank the people who have actually collaborated with me on this work. The dielectric constant stuff was done with my colleague Leo Liu and Javier, who has just joined our department as a Chancellor's Fellow. The polarization free energy stuff was done in collaboration with Richard, and a lot of the work has been done by Andrew and Cecilia, 2 of my PhD students. So Andrew, by the way, is looking for a postdoc position. So if you have any available or know anyone who does, please give me send me an email, and I'll be happy to point you in his direction. So thank you very much, and I'll be happy to answer any questions.
Miguel, many thanks for your very clear and most interesting presentation. Miguel, let me, before opening the floor for discussion, ask you one thing. For people that are not too familiar with the field, but we know that this matter of the polarizability is a really hot topic on molecular simulation nowadays. Everybody's working with it. Everybody's trying to develop approaches to input the polarizability in their molecular simulations. So your way of doing this is not the only one that is being proposed. I would like that you very quickly summarize the approaches that people are doing in literature, and why do you think that the approach that you are proposing here is better than the others that people are trying to propose?
Okay, so I think, to my knowledge, most of the other proposals are actually are based on increasing the complexity of the underlying model. So, for example, you can include polarization effects by having something called a fluctuating charge. So you can adjust the charge of the molecules on the fly during the simulation in response to the field. Okay. Of course, that means that you need to iterate over the charge in each step of the simulation. Okay, so again, the simulation becomes much more expensive. Another way to do it is put a point charge on the center of, say, let's say the oxygen atom in water. So you put a negative charge there, and you put a positive charge on the end of a spring, and that spring is adjusted on the fly again to respond to the environment. That turns out to be faster than the fluctuation charge, but it's still a lot more time-consuming than the normal models, and also prevents you from using very large time steps, which is, you know, it's a technical issue, but actually, again, lowers the speed of the computation. I think that I mean, I'm not going to say that my approach or our approach that we're using is the solution to everything, because in some cases, for some problems, it is actually better to use a more realistic model, okay? To use a polarizable model and to run a simulation with a polarizable model. The problem is when the simulation becomes, or when the system becomes too big and it grinds to a halt, you cannot actually run the simulation you want. In which case, I think using these post facto corrections is essentially a computationally free way of doing it, right? It doesn't take anything else except an Excel sheet to apply these corrections. And okay, a bit of literature search on experimental data at the moment. So it's really an interesting tool, I think, to improve predictions of models that already exist. But as I said already in my talk, perhaps a new way of developing new models, now taking already this into account. What do I mean by that? I mean that sometimes models are, the parameters are adjusted to fit properties over a wide range of thermodynamic states. And it might well be that they're essentially trying to cover too much with a very limited set of parameters. Whereas if you include the polarization corrections afterwards, you wouldn't need to fit these parameters in the same way. You would fit them to, say, for example, a given set of conditions, and then predict all the rest from first principles.
Thank you. So the floor is open for discussions. Introduce yourself before you ask any question. Who wants to do a question, to bring up something?
Yeah, I have a question, if I can hear. Miguel, your approach is the non-polarizable force field, no, plus corrections, right?
Mm-hmm.
Okay, so this is the best way, no, to get a better performance in the computer simulations, because you avoid this spring and to simulate these two partial charges. What do you think if we have a system in which we have a water with this explicit polarizable charges interacting with other particles without it? For instance, in case of ionoliquids, we can say that that we have a single point charge in the head group. But if we are thinking about the counterions, for instance, chlorides or bromides, both are surrounded by a first layer of water. So in that case, we should take into account this counterion with the water. The interaction between this and the polarizable water is not correct, right? If we don't take into account the polarizability in this water layer around the counterion, right? Yes,
I think that's a very interesting question. I mean, the whole issue of ions is very interesting. So first of all, to answer your question very quickly, if you have a polarizable water model, and that's mixed with a non-polarizable model for something else, let's say ionic liquid, then I'm assuming that the ionic liquid will be charged, so it will have charges. What will happen is that the water will respond to the field created by the liquid, the ionic liquid, but the ionic liquid will not respond to the field created by the water. Okay. Now, I'm going to argue that probably the latter effect is more significant than the former, right? I mean, the ionic liquid will generate a perturbation in the water structure, but perhaps the water is going to perturb a lot more the ionic liquid, typically because in solutions, the ionic liquid is going to be the minority component. If it's the opposite, then maybe it's not true what I'm saying. But in any case, you still have missing physics because you don't have the polarizability of the ionic liquid with itself and with the solvent. Okay, so that's the first answer. The second answer is, when you are entirely correct, when you have a solvation layer on an ion, then the polarization effects of the ion on the solvent are going to be much more significant in the first layer than in the right. That stands to reason, right? The local interactions are much stronger than the long-range interactions in terms of polarization. In fact, I think it's an open question how long-range polarization effects are, right? That's a researched field in itself. But I would say really that if you don't account for polarization in that first shell, then you are missing a lot of. And just to complete this issue of the ions, it's very interesting. We've not done any work on ions yet, but I'll try to find the reference. Some guys that we based some of our work on. Try to find where the reference is, somewhere here. Okay, so these guys, Leonti, Evans, Tuchebrukov, they actually applied this scaling factor. Now they've used, I think their scaling factor is slightly wrong, but that's a different story. But they applied this to correct the solvation free energy and the free energy barriers of ion interactions in water, and they obtained a much better agreement with experimental data by applying this correction. Okay, now I've seen some talks also by Panagiotopoulos and the Benedetti in some conferences about calculating solvation free energy of ions, right? And they are now using, again, scaled potential, scaled charges for ions to represent these interactions, precisely because of that scaling effect that I mentioned before, okay? So I think we're really in a situation where everything is coming together. It's like we're connecting the dots into a new approach of modeling these systems.
Yeah, that's right, because this can affect strongly the solvation of the counter ions, and it's important.
Absolutely.
In the assembly, or not only to obtain the thermophysical properties or the macroscopic properties, but using the simulation is an important fact to take into account. Yeah. Thank you, Miguel.
Anyone else? Any further questions?
Hi, hello.
Nicola.
My name is Nicola. I was, well, you kind of answered my previous question about ions. I've also seen in the literature where some people, for example, modify Berliner-Jones by adding a third power term to better account for solvation free energies and so on, instead of going through your procedure. What would you say in comparison to this?
Okay, so I think there are two questions really here. The first is, are the Lennard-Jones parameters of ion models the correct ones? In the sense that it's really difficult to calibrate them against experimental properties. Whereas for pure liquids, it's fairly straightforward to do. For ions, it's really difficult because all the effects are jumbled together. So you have the Lennard-Jones interactions, you have the polarization, you have the charges, okay? Now, what I think is that and again, we haven't done work on ions, but if I were to approach this problem, I would leave the van der Waals or the Lennard-Jones interactions for last. So I would try to represent first the electrostatics, the permanent electrostatics, then include the polarization in some approximate way. And finally, once this is done, if the results still do not match experimental data, then I would tweak and adjust the Lennard-Jones model, okay? Now, doing it the other way around, I think is not the best way, precisely because I think at the moment, the simple point charge plus Lennard-Jones models are missing some physics. So you first include the missing physics, and then if you need, you adjust the parameters. If you do it the other way around, you're sort of in a way, might be getting the right results for the wrong reasons, okay? And then when you try to predict, then all bets are off, okay? But again, you know, it's a more complex scenario than what we are dealing with in my talk.
And if I can have a second question as well, if you don't mind. I was wondering in your results, if you compared, because you compared against the classical non-polarizable force fields, and if you've compared your results to force fields with, for example, Druid polarization and so on, And if you get the same values for a lot less computational efforts, or are they still better, for example?
That's a very interesting question. I don't think there are extensive studies of dielectric constants using polarizable models. I found some from Mackerel's group, but only on a few compounds, and their polarizable models are slightly better than our corrected non-polarizable models. Not much, so the mean sign deviation is on the same order, but their models have less scatter, so they fall better on the line. I didn't show the data because it's just maybe a half a dozen points, up to 10 at most. Now, we have to bear in mind that they've adjusted the parameters of their polarizable models for each different kind of fluid to match the dielectric constant. Okay, so to me, it's no surprise that they get a better result. I think a fair comparison would be if you had a model that was a polarizable model that was fitted to exactly the same properties as the conventional models, and then compare that with the conventional models plus correction. I don't think anyone has done that. The other thing I need to add here is that if you look at this formula here, the top one, which is how you calculate this in like a simulation, you see that it's what we call in the simulation jargon a fluctuation property, because it depends on the fluctuations of a measurement, not on the measurement itself or on the observable itself. So similar things are like heat capacities or thermal expansion coefficients, etc. They are fluctuation formulas. In thermodynamics, they're essentially a first partial derivative of an energy. Okay, here is first partial derivative of the dipole. So what that means in practice is that it's much harder to converge these calculations than in a normal simple property like density or enthalpy. Okay, so typically all these calculations that I showed you before here, they have been based on very long simulations of tens of nanoseconds, even up to sometimes 100 nanoseconds, which are very long and are very difficult to achieve with a conventional polarizable model for a very large range of systems. So again, you actually need to use the classical models to get a converged value of dielectric constant, but then you get it wrong because you don't have the physics.
Okay. Okay. Sorry, can I have another third question? I just something that popped in my head, because you got your K value from methanol, didn't you?
Yes.
What happens if you have, for example, polyalcohols, or how is it still extrapolable? Or, for example, if you have more functional units, does the relationship break down?
Good question. I think this data set that I'm showing now, that phenol data set on OH containing compounds, I'm pretty sure it contains at least 2 or 3 polyfunctional alcohols. And it works well for those as well. I think there's an you can see clearly, I'll show you this one with the corrected one. There's an outlier here, and I think this is not a multifunctional alcohol. It's an alcohol combined with an amine, I think, so an alkanolamine. And so the alcohols themselves fall on this nice line, including polyfunctional alcohols. Now that may be fortuitous, okay? We are trying to work, as I said, with Richard, on ways to derive K from first principles, so that we don't have to fit to anything, right? And that's in the future, so I can't tell you what that will look like. But we are hoping that it will provide a more predictive approach. Yeah.
All right. Well, thank you very much. Huh?
Well, any last question? If this is not the case, I'm going to thank Miguel again for taking this time to present this work to us. That's been very instructive for all of us. I hope that you all have enjoyed as much as I did, and we will have a nice weekend, and we will meet again next week. Miguel, many thanks for this wonderful presentation and for being here with us this afternoon.
Thank you for the invitation again, and it was a pleasure.
Okay, see you. Bye.
Thank you. See you. Bye. Take care.
Thank you.